Where we left off was talking about different ways to show molecules. There's a lot of different ways in chemistry we can represent them. And one of the ways is just by writing out the formula. Another one is actually drawing a picture of the formula or sketching out what it looks like. So today we're going to sort of learn about how we figure out what a formula is based on some measurements. And this was the way that chemistry was done. Like all the major discoveries in chemistry were done like, 100, 200 years ago, where people in a lab would get a compound, they didn't really know what it was, and they would either heat it up or they would burn it or they would do something to it in order to change it, and then measure the amounts of whatever elements or compounds came out of it. And then from that, try and figure out what it was they had in the first place. So this is where we left off last week. We talked about an empirical formula and a molecular formula. An empirical formula is just basically finding out what's the simplest molar ratio between elements in a compound. And an example we've got here is benzene. Benzene is a very common organic compound, and this is the formula. It's got 6 carbons and 6 hydrogens. Now, if you were to look at what's the simplest ratio of carbon to hydrogen, it'd be 1 to 1. And so if someone, like, let's say, 150 years ago had a sample of benzene and they wanted to figure out relatively how much carbon and how much hydrogen was in it, pretty much all they could say was that it has equal amounts of carbon and hydrogen. But until you know how much a mole of that is, what's the mass of a mole of benzene, you don't really know what the molecular formula is. Same thing here, acetic acid. Anyone know when you come across acetic acid in your day-to-day business?
It's vinegar.
It's vinegar, exactly. Probably might be using it to cook tonight. So vinegar is just a 5% solution of acetic acid. So again, if you wanted to break down how much carbon, how much hydrogen, how much oxygen was in there, you would find out that for every 1 atom of carbon, there's 2 atoms of hydrogen and 1 atom of oxygen. But that's not the actual formula. That's the simplest ratio. If you were to figure out what the mass of a mole was, then you would figure out that the formula is actually twice as much of each one of those atoms. So we're going to figure out how it is we do that. Here's benzene. Benzene is really interesting because you're all going to be taking organic, right? Yes, you are. So when you take organic, you're going to find out that benzene is a really interesting way of putting itself together. So here we have double bonds, and here we have single bonds. And benzene is what's known as an aromatic compound. If you ever smell it, you will quickly find out why it's called that. It's really, really smelly. This ring system is, it evaporates very, very, very quickly. We say it has a high vapor pressure, and it's very strong smelling. So that's what benzene looks like. You can see it's just a clear liquid. Vinegar or acetic acid looks like this. And so this is what it looks like. Its structural formula is here. So if we were to draw it, that's the way the atoms are arranged in acetic acid. This is the acetic part. This is what's known in organic chemistry as an acetyl group, CH3. We call that an acetyl group. And this is the acid part over here, because this hydrogen leaves and increases the concentration of hydrogen atom or hydrogen ions in a solution, and that's what gives you pH. And so if we were to draw it as a ball and stick model, you can see there's a double bond here, single bond here, and this hydrogen, some of that hydrogen comes off. we say that's a weak acid because not all of it dissociates, just some. And we'll get into strong acids and weak acids a little bit later. So that's what acetic acid looks like. So if you were to get a question like this, we'll get questions like this, I promise. You're going to get, there's a whole bunch of them on the recitation, and you'll definitely be getting them on a test. This would be a classic example. So a sample of a carbohydrate. Anyone tell me what a carbohydrate is? Anyone remember their high school biology?
C6H6O12 O6.
That's a carbohydrate. Yeah, that's glucose. That's an example. That's an excellent example of a carbohydrate. More generally, it's basically an energy storage compound that we use to burn. We actually physically burn it in our bodies. When you say you're burning calories by running or whatever you're doing, you're literally doing that. You're burning up sugar in a lot of very small steps. And we'll return to that when we talk about something called Hess's law, where instead of just burning it in one step and creating CO2 and H2O, you take a lot of different steps and you can get a lot more energy out of it. So we get a sample of a carbohydrate, and it has oxygen in it, it has hydrogen in it, and it has carbon in it. So we need to calculate the empirical, we need to calculate the empirical formula, which is all we can do with this information. With this information right here, we know there's that much carbon, that much hydrogen, and that much carbon, oxygen, and hydrogen. So we know we can calculate what the simplest ratio is, but we will not be able to figure out what the molecular formula is until we have this information down here. So 1 mole of this compound has a mass of 180 grams. So we'll figure out what the empirical formula is first, and then we'll calculate the molecular formula. So let's go through how to do that. All right. So here's our information. So we have 53.3% oxygen. We have 6.67% hydrogen. And we have, was it 40.0% carbon? Yeah, 40.0% carbon. So what does percent mean? We sort of talked about this before. What does percent mean?
Divide by 100.
So if we divide it by 100, what do we get?
0.533.
But we get a fraction, right?
Yeah.
We get a fraction, exactly. The thing is, what can we do with a fraction? Because what we want to figure out is we want to take this information and we want to use it to figure out how many grams of carbon, how many grams of hydrogen, and how many grams of oxygen, because that's what we need. We need grams in order to do this calculation, because we need to figure out how many moles of each one there are. And the only way to do that is to figure out how many grams of each one there are. But I've got these percentages. So what am I going to do with a percentage? How am I going to convert that to grams? What would be a simple way to convert it to grams?
You take the mass and convert it.
Take what mass though? I don't have any masses. I just have percent.
Oh, you're not using the 180 grams of compound?
I don't have that information yet. I need to figure out the empirical formula first. So right now, I just need to figure out what's the simplest ratio of oxygen, hydrogen, and carbon. And all I have is a percent. So I need
the molar mass?
I have the molar mass. So the molar mass of carbon, we're going to use like simple ones right now. You can look it up. But so carbon is 12 grams per mole. Hydrogen is 1 gram per mole. This is like approximate. And oxygen is 16 grams per mole. So I can look that up off of the periodic table. That's no problem. My question is, what am I going to do with this? I can't, that's a percent. Well, I can't divide or multiply percent by anything to get me moles. How do I convert percent to grams? Anyone have any ideas?
We can start off with using 100 grams.
There you go. Exactly right. That's perfect. Because if I have 100 grams of stuff, I don't know what the stuff is, but if I have 100 grams of it, that means I have that means I have 53.3 grams of oxygen, I have 6.67 grams of hydrogen, and I have 40 grams of carbon. So all we've done here is just make the assumption, okay, I got 100 grams. And you could use any number. You could use 200 grams, you could use 1,000 grams, you could use 1 gram. But use 100 grams is much easier because you don't need to do any math. Because 53.3% of 100 is just 53.3. So that's why we use 100, because it's like super, super easy. And if we can make something easy, let's do that. So that's how much, so in 100 grams of my stuff, my carbohydrate stuff that I don't know what it is yet, that's how many grams of each one of those elements is there. Now I need to convert those to moles because grams don't interact with grams, moles interact with moles. So how am I going to convert that to moles?
Would you use Avogadro's number here?
Nope. Remember, I told you, I never want you to use Avogadro's number for anything ever. We only use Avogadro's number for if we want to calculate the mass of one atom, and that's not terribly useful. Or if we want to count atoms, and that's not terribly useful either. Since we can't weigh atoms, we can weigh moles though. We can get the mass of moles. So I want to convert these grams to moles. How am I going to do that?
You divide by the gram per mole values that we have.
Excuse me?
Can you divide the grams by the 12 grams per mole? And
We remember, never divide. Never ever divide, but I know what you're going for. So what should I need to multiply this by something. What am I going to multiply it by?
1 mole over 12 grams.
There you go, exactly. So why I never want you to divide anything is because I want you to put the units in there. Excuse me. So you wind up with the right units. Like this afternoon in lab, we were determining RF, basically retention factor. And so if you realize that you had units of millimeters or centimeters on the top and units of millimeters or centimeters on the bottom, they cancel out and RF becomes unitless. Same thing is true here. We want to end up with moles. So if we multiply something with moles on top and grams on the bottom, that guarantees we're going to get the number we want. So 53.3 divided by 12, what does that give us? How many moles is that?
Shouldn't it be 16?
Oh, you're right. I'm sorry. You're absolutely right. 16. I was looking at carbon. I was thinking about carbon. I'm always thinking about carbon. Yeah, 16 grams. You're absolutely right. So 16. So how many moles of oxygen do we have?
3.33.
3.33 moles of oxygen. Excellent. So hydrogen is just 1 gram per mole. So that's pretty straightforward calculation to do. 6.67 moles of hydrogen. And carbon, finally get my carbon, 12 grams. And how many moles of carbon is that?
3.33 moles.
Yep, 3.33 moles of carbon. Now, as you can see, one of the things we learned previously is that you have to have whole numbers of atoms in a molecule, right? There's no such thing, there's no molecule somewhere that has 3 1/3 atoms of oxygen, 6 2/3 atoms of hydrogen, and 3 1/3 atoms of carbon. That's impossible. But what we can do here is what we divide by the smallest number that's there and see if we get whole numbers out of it. And as you can see, if we divide everything by 3.33, this gives us 1, 2, and 1, right? If we divide everything by 3.33, so what we've done is in 100 grams of this stuff, that's how many moles of oxygen we have. That's how many moles of hydrogen we have. That's how many moles of carbon we have. So the simplest way, that's the ratio. So the simplest way of representing that ratio is 1 to 2 to 1. So we would say that the empirical formula is CH2O. That's the empirical formula. And remember, we don't put a 1 next to carbon or oxygen. Jerome, shh. We don't put a 1 there because the 1 is assumed. So CH2O is the empirical, that's the empirical formula.
So why you divide by 3.33? This is because the common between them?
Because we need to find the simplest ratio of the 3. I mean, we could multiply everything by 3, and that would give us 10, 20, and 10, but that's not the simplest ratio.
Okay.
Simplest ratio, the way you usually find the simplest ratio is divide everything by the smallest number you have. So the smallest number of moles we have is 3.33. So divide everything by that, and then usually, but not always, will usually give you the simplest ratio. Okay?
Okay.
So this is this is the simplest ratio we can show. But we're not done because this is the simplest formula. We don't know if it's the right formula. It might be C2H4O2. It might be C3H6O3. We don't know what it is. We know that this is the simplest ratio. We don't know what the absolute ratio is. And the only way to determine that is through the molecular mass. Anyone remember what the molecular mass was of this molecule? How much did a mole of this stuff weigh?
180
180 what?
grams.
There you go. You gotta have a unit. Okay, so that is our mass. So 180 grams in 1 mole. How much would a mole of this weigh? How much would a mole of that weigh? Or what would be the mass of that? Someone want to calculate it for me? So you've got 1 carbon, 2 hydrogens, and 1 oxygen. So if that's 12, and that's 2, and that's 16, how much would 12 grams, 2 grams, 16 grams. How much would 1 mole of this, how much would 1 mole of that weigh?
30 grams.
30 grams per mole, right. So the molar mass of this is 30 grams per mole. And then we know the actual mass is 180 grams per mole, which is 6 times more, right? So the ratio of the mass, of the molecular mass to the empirical mass is 6. which means we have to multiply everything in the empirical formula by 6. So we take the oops. Let's move this out of the way. So we take the CH2O and we multiply each one of those by 6. So C1 becomes C6, H2 becomes H12, and O becomes O6. And so our molecular formula is C6H12O6, and that is glucose, which is one of the simplest carbohydrates. Okay? So we're going to be doing lots more of these in recitation tomorrow. But yeah, that's basically how you do that. First, you figure out the simplest ratio by assuming you've got 100 grams of whatever. Convert the percent to grams, get the simplest ratio of the atoms in there, figure out how much a mole of that, what the mass of a mole of that would be, and compare it to the actual molecular mass. And it'll be some ratio. Hopefully a whole number ratio, like 2, 3, 4, 5, 6, 7, something like that. Okay? Any questions?
You get 30 by assuming or you calculate?
What am I assuming?
The 30 gram, 30.
No, we didn't assume that. We calculated it. 1 mole of carbon is 12 grams. 2 moles of hydrogen is 2 grams. And 1 mole of oxygen is 16 grams. So CH2O, if that was the formula of my molecule, it's the empirical formula, that would weigh 30 grams per mole. If that's a molecule. But it doesn't weigh 30 grams per mole. It weighs 6 times more. So everything, all the atoms in that molecule, there must be 6 times more of them in the actual molecule. So we multiply everything by 6. So C1 becomes C6, H2 becomes H12, and O becomes O6. Okay? We'll go over this a lot more tomorrow as well. All right, I'm going to clear that. We'll continue. So another way to think about these molecules is to talk about isomers. Anyone know what an isomer is? Have you heard of the term isomer before? Maybe you've heard about isometrics or something. It's right there. An isomer is 2 compounds that have exactly the same chemical formula. As we know, atoms can arrange themselves in all kinds of interesting ways. Generally in covalent compounds, because in covalent compounds we can form single bonds, double bonds, and triple bonds. They can arrange themselves in all sorts of different ways. Like here's an example. So the acetic acid we just discussed a minute ago, and another molecule called methylformate have exactly the same formula, C2H4O2. But they have completely different structures and completely different properties because they're put together differently. So here's what they look like. So acetic acid is here on the left. This is the acetic acid we showed before, and this is the acid part. And then over here, notice that it's different. They both have a methyl, they both have a CH3 part. But this part is different. Here there's a carbon-carbon bond, and here there's a carbon-oxygen bond. So they're different molecules entirely, and different chemical properties. So we call those isomers. So now we're going to start. Now we get to the real meat of the course that I really I like talking about. So yeah, stop me, or else I'm going to blather quite a lot. But we talked about the periodic table, and of course, Jerome. So the periodic table, I think, is the single most important thing in chemistry because it basically has all the information you need to answer pretty much any question. And so if you have a good periodic table, that's pretty much all the information you need to answer about like 80, 90% of the questions. And so the way it's organized is unique, and the way it's organized gives you a lot of information. So you've probably heard of Dmitry Mendeleev before. Everyone's heard of Mendeleev, hopefully, right? The famous Russian chemist of the 19th century. What most people don't realize is that a German named Lothar Meyer came up with the sort of same kind of table at the same time, but nobody remembers him anymore. And the reason is because Mendeleev really liked to self-promote. He was not shy. He was known as a player in those days. He was a big baller. And so he used to get into arguments with people, and he would like shout at them and yell at them. And he was just like, and the problem with Mendeleev, he would yell at people and say he was right. And the problem was he usually was. And so that's why he had such a reputation, and why we know about him today. And Meyer was a nice guy, and we know what happens to nice guys, right? So the way, anyone know why it's called the periodic table? Why do we call it that? Ooh, quiet. Why don't we just call it the chemical table? Why is it called the periodic table? Anyone have any ideas? What does periodic even mean?
Something repeats.
Yeah, exactly. If something repeats at regular intervals, it's basically, it means it's predictable. So if there's a periodicity to something, it means you see the same thing after a certain period of time, like a clock. Like, you know, it hits 12 once an hour, you know, and you can predict it. And why do you think it's called the periodic table?
Because we put the element that has same.
Yeah, you're onto something.
Because chemical properties repeat.
Yeah, exactly right. Yeah, the chemical properties of elements repeat themselves. There's what we call a periodicity to it. You can basically predict what are the chemical properties of an element based on where it is in the table. So, for example, right here, there's a reason why lithium, sodium, and potassium are arranged on top of each other on the periodic table. They're all shiny, they all conduct heat and electricity, and they have very similar chemical properties. For instance, they all explode when you throw them in the water. They all form ions with a +1 charge. So they're very, very similar elements. In the same way, calcium, strontium, and barium are shiny, conduct heat and electricity, but they're less reactive than these three. They're not quite as reactive. If I could take calcium and throw it into water, it's not going to explode. It'll slowly dissolve, but it's not going to explode. And they all, when they ionize, they form +2 ions. So they're all metals. They all have very similar chemical properties. And so the way they're arranged in the periodic table shows you that. And so it's extremely helpful for trying to figure out what kind of compounds elements are going to make. It was really important. I'll show you a little bit later how Mendeleev used this information to predict elements that hadn't been discovered yet. He was so sure he had put these elements together properly. Well, I'll let you get to it. It's a great story. Well, I think anyway. Anyway, so this is, you've seen this 1,000 times. And so, like I said, it is arranged in ways that elements on top of each other are very, very similar. And so over here, those were the elements that all form +1 ions, strangely, in group number 1. All of these elements form +2 ions, interestingly, in group number 2. And then over here, these form +3. And then as we go further and further to the left, they start to form negative ions. So we have positive ions are formed over here. Negative ions are formed over here. All of these elements form -3. These elements form -2. All of these elements form -1. And so the arrangement of them tells us something about each one. And we will learn in the next chapter exactly why that is. And so if you could put those two things together, basically you've got the whole class. And we're going to come back to the periodic table a whole bunch. This was the original periodic table that Mendeleev was dealing with. This was before he started putting things together. This was a really old periodic table. And you can see the way it's arranged is by mass. It's not by number, because at that point, nobody knew what electrons, protons, or neutrons even were. But they could measure the mass of atoms fairly accurately. So you can see hydrogen is 1, that's true. Carbon's 12, oxygen's 16, fluorine's 19, magnesium's 24. I mean, they got all these numbers right. And so they're just organized like smallest one first, biggest one last. But there's no organization. Sorry, guys. Quiet. Cammy, come here. Cam. I got nobody else to grab them. Just hang on for a second. Man, that drives me crazy. Anyway, yeah, you see there's no organization here. It's just smallest first, biggest last. So we can't, just based on this organization, we don't know what the chemical properties of any of these things are. We just know that some things are big and some things are small. It doesn't tell you which ones are gases. It doesn't tell you which ones are metals. It doesn't tell you which ones are non-metals. It doesn't tell you anything. So this wasn't terribly helpful. So elements were first arranged by just increasing mass. And then it was Mendeleev and Meyer who figured out that those properties are periodic. And so maybe if you arrange them in such a way that elements that were like each other were put together, and other elements that were like each other were put together, it would make a lot more sense and be a lot more useful. So this is the man, the legend. There he is. And so, yeah, he had awesome hair. You can see a lot of chemists during this time. Einstein didn't have the beard, but he definitely had the hair. Mendeleev had it all. So, yeah, he's probably the most famous Russian scientist there is. And so you can see behind him that this was the original way he organized the metals. So you can see here, he's got hydrogen, lithium, sodium, potassium arranged together. He's got beryllium, magnesium, and calcium arranged together. And later on, it would turn out that not only that was the better way to do it, because these all had similar properties, but after the electron was discovered and the way the atom is organized, it turned out that the organization of the atom and the organization of the periodic table meshes exactly. And so, that's why he was seen as the man. And it was before the Nobel Prize was invented, or he definitely would have won one. So here's some of the essential pieces of the periodic table, things that I'll be referring to a lot. And so you may want to just, remember what some of these are. So there's a main way the thing is organized is in periods and rows. So periods go across, or periods go up and down. Sorry, periods are the rows, they go across. Groups are the columns, they go up and down. So elements in groups are alike. And elements that are in a period are not particularly alike, but they do have something in common, and we'll get to what that is. So the vast majority of the periodic table are metals. Like 80–90% of the periodic table's elements are metals. Very few non-metals and even fewer metalloids. And so you can imagine, what are metalloids? Metalloids are elements that have some metallic properties and some non-metallic properties. And then these are some of the some of the most important groups. Halogens, which are group 7, right next to the noble gases. They all form -1 ions. The noble gases, all gases, and none of them form compounds very readily. The alkali metals, the alkali earth metals. I'll talk a little bit about lanthanides and actinides. Those are the transition metals. And SP, D, and F we'll be talking a lot about. And SP, D, and F are basically, those are the different orbitals that electrons are in. We're going to talk about that next chapter. And the reason that's so important is that is how the periodic table was organized. When the periodic table was put together, it made perfect sense, but nobody could understand why it looked like it did. Like why is there this huge gap between of transition metals? There's like a whole bunch of them. There's like 10 of them until you get to the metalloids. And these lanthanides and actinides, there's like 15, 16 of them in a group. Why is that? And we'll learn why that was, because of electrons. So just like I said, vast majority are metals. Everything on the left side is metals. Everything in the middle, metals. We really only get to the non-metals when we get to these stair steps. So if you have a periodic table, I assume most of you like either have a textbook or you may have a periodic table you bought at the bookstore or whatever, usually has this stair step on it here. This one right here. That is basically the breakdown of the metals and the non-metals. So all metals on this side, metalloids on the steps, and then everything else are non-metals. Everything to the right of the stair steps are non-metals. The ones right on the steps are metalloids, okay? And we'll go into some of the ways that metals and non-metals are similar to each other. So broad classes, these are sort of the broad classes of elements. Our main groups are here. These two groups and these groups. We say they're the main groups because their chemistry is extremely reproducible. It's pretty much the same all the time. All of these metals in group 1 are +1 ions. All of these metals in group 2 are +2 ions. And basically all of these metals react and non-metals react the same all the time as well. In the middle, we have these transition metals. And we mentioned before, but the transition metals, hey, Jerome, make me chuck a towel at you. So the transition metals basically mean they take on different charges depending who they're bound with. Sometimes they're +1, 2, 3, 4, even +6. And so they can take on a whole bunch of different charges. And then down here on the bottom, lanthanides and actinides. You may have heard of rare earth. Who's heard of rare earth metals? kind of important these days. No one's heard of rare earth metals before?
Heard of
Yes,
the
and magnet.
Yeah, magnets. Yeah, big time. You can make extremely strong magnets out of things like holmium and erbium. And where's niobium? Niobium's in here somewhere. Or praseodymium. They form these extremely strong magnets. And they have, they're also found in cell phones and like batteries. Like pretty much the whole world now runs on these rare earth metals. And it's kind of interesting that one of the places on Earth that has the most rare earth metals is Afghanistan. Kind of interesting that the US military has been there for 20 years. One of the reasons may be because of all those rare earth metals that are present there. We're not really going to talk much about the rare earth metals because they're pretty weird and they form these bizarre compounds that's a little beyond what we're trying to get to. But if you're interested in any of that stuff, there's some, yeah, I can link to some videos on the rare earth metal because they're really interesting. Okay. So these are the basic classifications. Like I said, nonmetals on the left, with the exception of hydrogen. Hydrogen is one of those weird, hydrogen's a weird element anyway, for a lot of reasons. Hydrogen has metallic and non-metallic properties. It can be a metal and become positive. It can also be a non-metal and be negative. It's one of the few elements that can do that. So these are all metals. As I mentioned, on the steps, these are our metalloids, one of them being silicon. And then these are our nonmetals over here. So basically, all of the nonmetals that we're talking about that are reactive are just these few. This is it. The vast majority of atoms in your body that are doing everything are those right there. That's it. So it's kind of important to know what the nonmetals are, because that's all of them are right there. And that's basically the building blocks for, you know, maybe 95% of the molecules in your body. So just those few. So if you're going to take organic or biochemistry, you're going to be spending a lot of time working on those. So periods, arranged horizontally. So we have period 1, there's 2, 3, and you just go across. And it's the number of electrons, and we'll get to this, but it's the number of electrons in each shell determines how many how many elements are in your period. For instance, period 1 just has 1, 2 elements in it. There's 2 electrons in the first shell. Period 2 has 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons in the second shell. Period 3 also has 8. There's 8 electrons in the third shell. The fourth goes all the way across. There's 16. There are 16 electrons in the fourth shell, and so on. And so it was the arrangement of the periodic table that actually led to people figuring out quantum mechanics. I know it may seem bizarre, but yeah, it was the periodic table that told people when they were working on these bizarre mathematics for quantum mechanics that they must have had it right. Because when they did their calculations, and I'll show you Schrodinger, you probably have heard of Schrodinger before. When Schrodinger did his famous calculations with his equation, Schrodinger's equation, when he finished it, he saw these numbers, 2, 8, 8, 16, 32, and he said, oh, that must be right. And so, all because of the periodic table. So we'll get into that next chapter. It's fun stuff, believe me. Now, groups, I find groups are more important because it's groups going up and down those tell you what the properties of them are. And they're very, very similar. Like these are the alkali metals here, group 1. Like I said, they all form +1 ions. These are the alkali earth metals, group 2. They all form +2 ions. Group 7, those are the halogens. They all form -1. Group 6, -2. Group 5, -3. And then you have group 3 and 4. And there's a reason for that. The way their electrons are organized in their shells predicts what sort of chemical periodicity, what kind of chemical arrangement they're going to have. It's sort of basically, if you see what the arrangement of electrons are, you can easily predict what its chemical properties are going to be. So, if you have a periodic table in front of you, hopefully you do, which list of these elements includes those in the same group? So, in other words, these will be elements that have the same chemical properties because they're in the same group going up and down. Someone tell me which one it is.
The third one.
Yep, the third one. Which group is that? I think it's 2 or 3. 3, right? Or group 2? Group 2 or 3? I can't remember.
It's group 13.
Oh,
3.
I was thinking period. All right, let's go to the next one.
3.
3.
3, yes, thank you. Which list of elements has those in the same period or row going across?
The last one.
Yes, those are all metals, transition metals, in fact, iron, copper, and nickel. So these are some of the famous groups of the table. These are the ones you should, oh my God, I killed them. These are some of the groups of the periodic table you should become. Okay, I'm just going to pause for a second. Where can I pause? There's Zoom. Yeah, so these are the groups we're going to be coming back to over and over and over and over. So you might as well some of them. So the alkali metals, group 1, alkaline, earth metals 2, some of the more famous transition metals, halogens last, halogens next to last, noble gases last. And these are some of the ones we're going to be talking about most that basically show up the most because they're common metals. They're common elements in Earth. In fact, the bigger and bigger you get the elements, the less and less common they are. And anyone know where the elements come from? Where did they originally come from?
Rock.
They were somewhere else before they were in rocks. What produces elements? There's something in the solar system that produces elements.
The sun.
The sun, exactly. All of these elements are produced in the sun up until iron. The sun can only, our sun can only produce elements up until iron. Everything else basically needed supernovas to be produced. So all of these elements bigger than iron took supernovas exploding. for them to be released. So massive things like, you know, two suns crashing into each other, that sort of thing. That's the kind of energy you need to make these big elements. So whenever I think about that, it's like, wow, you know, it's amazing they're here at all. So hydrogen, lithium, sodium, potassium, we'll be dealing with those a lot. Those are very, very, obviously hydrogen, super, super abundant. It's the most abundant element in the universe. And then hydrogen and helium are the basically two most abundant elements in the sun, and it's the fusion of those that gives rise to everything else up till iron. So these are the most halogens we'll be talking about most: fluorine, chlorine, bromine, and iodine. I had a professor, anytime I said iodine, a professor used to, like, you know, yell at me. So now I say iodine, even though it sounds weird, right? Because everybody else says iodine. Oxygen and sulfur in group 16, nitrogen and phosphorus. These are all really important elements in your body. Like, you know that if your plant runs low on nitrogen or phosphorus, it's not going to be good for it, right? These are essential elements. Carbon, silicon, and I want to point out three here because they're kind of important: aluminum, zinc, and iron. I just want to point out those three. Notice how they're sort of in a staggered line like that. These three are unique in that aluminum is always +3, and that makes sense because it's in group 13 or group 3, so it has a +3 charge. Zinc is always +2, and silver, Ag, is always +1. Even though zinc and silver are transition metals, their charges do not vary. So zinc is always +2, and silver is always +1. So if you ever wonder about these charges, you can see they're all in a row. Aluminum's right next to the stairs, so you can see that. So aluminum +3, so +3, +2, +1. If you ever, because sometimes on a test or something, you'll be wondering, oh damn it, what's the charge of whatever? I don't know what it is. It's a silver. It's a salt that has silver in it and chlorine. I don't know what it should be. Well, silver is always +1. Chlorine's always -1. So the formula for silver chloride is always going to be AgCl. Just a little thing to remember. So next chapter, we're going to be talking about electron configurations. And I mentioned a little bit ago that Schrodinger pretty much knew he had nailed it when he looked at the periodic table, and he saw that all of the elements that are in the same group have the same electron configuration. So in other words, everybody in group 1, its outermost electron is in an s orbital, and there's one of them. All of them. And all of the halogens in their outermost shell has a p orbital, and there's 5 of them. Every single one. And the noble gases all have p orbitals in their outermost shells, and they all have exactly 6. And the fact that fluorine, chlorine, oh, there's a typo in there. It's not beryllium. It's supposed to be bromine. So fluorine, chlorine, bromine, iodine, they all get one more electron, and they put it in P5. They add another electron so that it's P6, and now they look like noble gases, and they're very, very stable. So basically, what this means is that all the elements are trying to get, let me just clear this, all the elements are trying to get to here. They're all trying to achieve that stable configuration. That's why everybody either loses electrons or gains electrons. They all want to look like that, because that is the most stable configuration of electrons you can have. So these on the left, they lose one. Once they lose one, they look like the nearest noble gas. All of these on the right, they gain one, so they could become the noble gas close to them. And we'll talk more about this in the next chapter, but it basically explains precisely why some elements are metals and some elements are non-metals, and explains exactly why they lose or gain the number of electrons that they do. So if you can put all of this together, hopefully I'm going to try and teach it that way. If you can put all this information together, hopefully it sticks a little more, because I can't retain information unless I got hooks in it, that sort of makes sense. And it's the fact that this explains what we see in chemistry so well, it helps me remember it a lot better than if it's some just arcane table with a bunch of numbers in it that I don't understand. But we'll have time to go over this more. So here's something I sort of alluded to a little earlier when I talked about what a mad baller Mendeleev was. So in his original table, there was a gap right here. There was a hole right there. Oops, let me go back. So there was no element here. In fact, there was a bunch of elements missing, because at the time that Mendeleev came up with the periodic table, there was only about 60, 65 elements discovered. And now we've got we're up to 118. So we've discovered a lot of them since then. So it made sense that there were a lot of elements that hadn't been discovered yet. And so when he published his periodic table, and there's these big holes in it, and people were getting on his case, it's like, hey, Alexander, what's up? Or Dimitri, what's up, man? There's this hole there. There should be an element there, and there isn't. Isn't that a hole in your model? And he went, no, it isn't at all. And so what he did, there he is again. What he did was predict that there was going to be an element there. So again, this is silicon right here. So this is silicon at 14, and this is germanium. And germanium hadn't been discovered. Anyone want to take a real wild guess at which country germanium was discovered in?
Africa.
Where do you think?
Africa.
Germanium.
Germany.
Yeah.
Canada.
A little bit. Yeah, so a German discovered germanium. So, because when you discover something, you get to name it whatever the hell you want. So, a lot of for instance, Mary Curie discovered polonium. She's Polish, and so when she discovered polonium, that's what she decided to call it. So there's a hole there, and so what Mendeleev figured, using the fact that he put these things together, he said there is an element there. We just haven't found it yet. And what it's going to have properties very similar to silicon. And he went on, he said it's going to be bigger than silicon, but it's going to have very similar properties. And so this is what he predicted. He called it eka silicon. Eka, I think, means bigger or next. And so he predicted that this element would weigh about 72 grams per mole. He predicted its density would be about 5.5 grams per centimeter. It predicted its specific heat, and we'll get into specific heat when we talk about thermodynamics. He figured out it would have a high melting point, what its color would be, that if it formed an oxide, it would have the formula X for whatever the element was going to be called, O2. He even figured out what the density of that oxide salt was going to be. And he figured out what when it reacts with chlorine, it's going to have 4 chlorine atoms, And this is what the density of the chloride is going to be. And he was exactly right in all of them. And so 15 years later, when germanium was actually discovered, and they went over and did all the calculations and measurements and everything, they found out that Mendeleev was absolutely right about everything he predicted. And so that basically shut everyone up big time, that Dmitri knew what he was talking about. And also, that was pretty much the end of the argument that the periodic table should be arranged in any other way. That was it. Oh, okay, yeah. Just because it made such a strong prediction that one element is like another one. And that you could make these predictions and be absolutely right. So that was pretty much the end of anyone thinking the periodic table should have any sort of other arrangement to it. Any questions about how Mendeleev was able to make these predictions and how they turned out to be very accurate? Do you understand how he made the predictions in the first place? Basically said it was going to be very much like silicon, only slightly bigger, then just did the calculations. If it's bigger than silicon, this is how much bigger it's going to be. And so its density is going to be this rather than, so you're just able to make those calculations and, you know, obviously made the calculations very well. So these are the different classification of elements. We talked about these at some length before, so we can go through these fairly quickly. So we know that metals, they're shiny, they're malleable, meaning you can sort of work them into different shapes, and they conduct heat and electricity very well. Non-metals aren't particularly shiny and are crappy conductors of heat and electricity. And metalloids are sort of in the middle. You know, they conduct heat and electricity somewhat well, and they possess some properties of both. And I think I mentioned that silicon, the reason why silicon is a semiconductor is because it conducts electrons like a metal can, but it doesn't conduct them very quickly like a non-metal. And if you're designing a computer and you're counting electrons, that's what you want. You want the ability to count each one. And so if they move too fast, you can't count them. If they don't move at all, you can't count them. So with a semiconductor, you can count them. You can actually count each individual electron coming and going. That's why silicon is so important for the computer industry.
So silicon is metalloid?
Yes. Yeah. So silicon is the classic metalloid. Mm-hmm. Because it has it's metal in some way and it's non-metal in other ways. It's not particularly shiny. It's a little shiny, but it's also brittle, like a non-metal. You can't. It's not particularly malleable. It breaks, right? You can't mold silicon into a particular shape very well. It breaks easily. And so with metal, you can just pound on it and flatten it out. You pound on silicon, it just smashes into pieces.
Okay.
And we also talked a little bit about molecular ionic compounds. And so we'll just sort of want to, we talked about it basically when we did the recitation. Now we're finally getting to it. So in ordinary chemical reactions, now chemical reactions, the nucleus of the atom stays the same. In a nuclear reaction or an atomic reaction, the nuclei are different. So either particles are added to it, the nucleus gets bigger, or particles are emitted from it, and the nucleus gets smaller. But that's a nuclear reaction. In a molecular ordinary reaction, only electrons move back and forth, just the electrons. The nuclei themselves stay exactly the same. So electrons participate in these reactions by doing three things. You can either gain electrons, and if you gain electrons, what kind of ion do you become?
Negative.
Mm-hmm. Negative ion, what do we also call them? You remember the name?
Electron.
Anion. I think someone said anion. Yeah, those are called anions, a negative ion. So if you lose electrons, what kind of ion do you become?
Cation.
Cation?
Cation. Yes, cation. And cations are what charge?
Positive.
Positive. Or in the with nonmetals, when nonmetals react with other nonmetals, they share they share. It's so beautiful. So they share electrons back and forth. So each atom has their own electrons that they keep to themselves, and they have some electrons that they share back and forth. And for each pair of shared electrons, pair of electrons, or two electrons, is one bond. So a single bond is two electrons being shared by a pair of atoms. A double bond would be four electrons being shared back and forth, and a triple bond would be six electrons being shared back and forth, each one being a bond. So ions, you get cations for positive charge, anions are negative charge. And remember, in an ionic bond, the electron is lost. The electron isn't shared. One atom gets an electron. It becomes negative. The other atom loses an electron. It becomes positive, and they don't get it back. So once a neutral metal ion, and it's always the metals that loses electrons, those metals don't get it back. They become ions. You would need to add electrons back, and that's what actually happens in a battery. When you're running a battery the other way, the metal that's in the solution gains electrons, becomes a metal again, and attaches back to the cathode, right? So you remove electrons, you get a cation, add electrons, you get an anion. Yep.
Professor, I want to make sure, when it's shared, it's considered as neutral?
Every molecule is neutral.
Okay.
A covalent, that's a covalent bond when they're shared. So there's no charge. None of the atoms are charged in a neutral covalent compound.
No, I'm talking about the slide before this slide.
Oh, this one?
Yeah, this one shared. It means neutral or just?
Neutral, yes. Both those atoms would be neutral. There's no charge. But there can be covalent ions. I'm not saying that's not possible, but a neutral compound has the same number of total protons and total electrons. In an ionic compound is also neutral, meaning that all the positive charges and all the negative charges have to add up to zero. But in a covalent neutral compound, there are no charges. There's no ions in it. They're sharing electrons. So no one's lost an electron, no one's gained an electron, they're being shared. That's the difference. We can talk more about it if you want to, but yeah, it just means they're shared, they're not taken. So this is how cations are formed. So remember, forming any ion just means electrons moving back and forth. We don't move protons back and forth, because remember, if we move protons back and forth, we're creating new atoms. We don't do that. We're creating new elements. So it's only the loss of electrons that leads to the formation of a positive ion. So here, neutral magnesium metal has the same number of protons and neutrons. And then it loses two and becomes a plus two cation. And believe it or not, this is actually more stable. The plus two is actually more stable than the equal number of protons and electrons. And we'll explain why that is in the next chapter. It may seem unfair. Oh, these poor metals are always giving up their electrons. Well, they wouldn't give up their electrons if it wasn't stabilizing for them to do so. Same thing with the nonmetals. they gain electrons. And so just the nonmetal by itself is extremely unstable. Just nitrogen by itself basically doesn't exist. You don't see nitrogen atoms by themselves. What you do is you see nitrogen molecules. N2, that's very stable. N2 is extremely stable. So when it forms an anion, it gains those 3 electrons and it gets to 10. Interestingly enough, notice the number of electrons that each has when it's stable. Nitrogen gains 3 to get to 10 and it's stable. Let me go back. And magnesium loses 2, interestingly, to get to 10. There's something magical about the number 10, and we'll learn what's magical about it in the next chapter as well. We've only got a couple minutes left. I'm just going to do a couple more and then take some questions. So we'll just do this exercise and we'll call it a day. So oxygen has an atomic number of 8, right? So that means something about how its atoms are organized. There's a mass number of 16. So the oxide ion is O minus 2. So this is what the oxide ion, it's oxygen minus 2. So the question is, how many protons, how many neutrons, and how many electrons are in that particular ion? You should be able to tell from the number of protons and neutrons and electrons just from that information. First of all, how many protons does it have?
8.
8.
Yeah, it's based on the atomic number. So right there, we can eliminate, not this, whoops, no, I screwed that up. Yeah. But, damn it, I should have had the, yeah, so, yeah, automatically we know it has to have 8 protons, the atomic number. That defines the element. So if it's oxygen, it's got to have 8 protons. It doesn't matter what isotope of oxygen it is. It doesn't matter what charge the oxygen has on it. It's got to have 8 protons. Now the mass number then tells you what's the mass of the nucleus. In other words, if I know how many protons there are, I know what the mass is, I can figure out everything else must be neutrons to go into the mass number. So it must, if it's 16, it's got to have the same number of neutrons. And the fact that it has 2 more electrons, it has 2 more electrons in its ionic form than the neutral ion does. So if the neutral ion has 8 protons and it has a charge of 2 more, it has to have 8 electrons to begin with, and then we add another 2 for a total of 10. And so this is our answer here. All right, so it took a while to get to this, especially with all the dog barking. I apologize. So any questions about this so far?
Just I want to make sure when we add 2 electron, it will not change the amount of proton. It's gonna be same 8.
Has to be same. Has to be the same, because if we change the number of protons, it's not oxygen anymore. If we take a proton away, it's now nitrogen. We take a proton away, it's not oxygen, it's nitrogen now. And if we add a proton to it, it's now fluorine, sorry, it's fluorine. So N is 7 and fluorine is 9. So if we add a proton, it now becomes fluorine. It's completely different chemical properties. Its own anything, any ion, remember, an element is solely defined by the number of protons. That's it. Just not electrons, not neutrons, nothing else. Just protons. So the atomic number tells us what the element is. And the only thing that defines a an element is the number of protons it has. That's it.
And same thing with the neutron, it will not change, it's gonna be same.
No, an element can have different numbers of neutrons. That's what's called isotopes, right? So we can have regular water with H2O, and we can have heavy water with D2O. The only difference is deuterium has one more neutron than hydrogen, but it's the same. It's basically the same stuff. Both makes water because it's still hydrogen. It's just heavier. And so we have different isotopes of oxygen too. There's some oxygen that has 7 neutrons. Most of it has 8 neutrons and some has 9. But they all have the same number of protons. Any other questions? Yeah, I'll try and get a handle on this Zoom thing. Luckily, we didn't break down and explode this afternoon, so good for us. But yeah, I'll try and get the lab up as soon as I can, because I know a lot of people are having computer issues of their own this afternoon, and we're trying to get into the lab. Probably the same thing with the lecture too. So hopefully we can, the Zoom will get a little more as time goes on. If anyone's having trouble, yeah, let me know. Just drop me a message, and I'll try and get the lectures and exercises and everything posted a little faster to help you out. So tomorrow, recitation 3, I posted that this morning, so you can have a look at that. Basically, we're going to be looking at what we talked about today, calculating molecular formulas and still doing more gram to mole calculations, because you really need to get good at those. So anything else before we go?
I have a question about lab.
Okay.
So
Today's lab?
no, the first lab that we did.
Okay.
I just want to make sure that we're just turning in the post-lab questions and then like the purpose and stuff like that, right? And just putting it into one sheet.
Whatever you turn in has to have, you know, your name, the date, the title of the experiment, the purpose of the experiment, the procedure of the experiment, the results from the experiment, and the discussion. And so if you want to do that all by yourself, that's fine. If you want to use the sheet, that's fine. But you need to have all those sections in there. So if you're missing any of those, you're going to lose some points on the report.
Okay. All right.
Yep. Yes, you don't need to turn in both. Is what I'm saying. You can use the sheet as a guide, but just add the missing parts to it.
Professor, I have a question about Tim's lab. Will you be uploading that video today, or would it be on Saturday?
I'm going to try the one for the lab today. Yeah, I'm going to try and get that done tonight.
Oh, okay.
Yeah.
Thank you.
Yeah, I think I found the file. It was corrupted because the computer crashed. But I think I'm going to be able to convert it into something that's actually usable. Fingers crossed.
Okay, thank you.
Yeah, no problem.